Hello students, welcome to my lecture. In this video, I will discuss a small concept which is related to the semiconductors. The concept charge neutrality equation in a semiconductor. Okay, so let's try to understand the few words here. What is the meaning of donor atoms? Donor. So generally fifth group elements. So fifth group elements will act like a donors. For example, phosphorus, arsenic, antimony. So all this will act like a donors. They donate the electrons. So donates. So for example, I am taking a phosphorus. Phosphorus will donate one electron. So it is donating one electron. So once it donates the electron, it becomes positively charged ion now. See, this is atom, remember. Now this is ion. Okay. Similarly, what is the meaning of acceptor? So obviously here you will add third group elements. For example, bismuth, aluminium, gallium, indium and so on. So actually say for example aluminium. So what happens here? It is acceptor. It is taking an electron. Okay. It is an absorbing. Or otherwise you can say that it is giving a hole. It is giving a hole or accepting electron. So I can write this will be, it is giving a hole. Hole is the positively charged. So then I can write it will be aluminium minus. So see here it is atom. Now it is ion. So here it is extra electron. Here it is extra hole. Extra hole. So if you are adding more number of this, just for understanding purpose, for I write only for one atom, but generally we will not add one atom, very large in number we will add. Correct? So that means donor, let's say ND will represent the density of donor atoms. That will be equal to, so it is creating the number of extra electrons plus the same donor now positive ion. I can write like this. Similarly here, number of acceptors will be equal to, they are creating the holes, number of holes plus number of acceptor ions. This I write for the charge. This I write for the charge. If you want to multiply with E, you can get the charge densities. So remember, this is the neutral atom. Neutral atom. And of course, this is also the neutral atom. Obviously, here this will be the electron means negatively 1. So this phosphorus will be the positively 1. Okay. So negative and positive. become again neutral. Similarly here, it is a neutral, this is hole is the positive and this aluminum will be the negative, then again it will become the neutral. Okay, it is clear. Now we will talk about, so what is the meaning of compensated semiconductor? What is the meaning of compensated semiconductor? Now I talk about compensated semiconductor. What is compensated here? So generally if I take a semiconductor, it consists both donors as well as acceptors. So a semiconductor consists both donors as well as acceptors. So is a type of semiconductor in which it contains both donor as well as acceptors. So suppose if I say here it is the donor, so and here it will be the acceptor. So when there is a donor, so I'll call it the donor atoms which donate. I call it the acceptor, it will be the Na. Okay, so in a compensated semiconductor, number of donor atoms will be is equal to number of acceptor atoms. Okay, so in a compensated semiconductor, Nd will be is equal to Na. So, and again one more important thing I assume here, the complete ionization will occur. Complete ionization. I will consider complete ionization. So donor atoms and acceptor atoms, every atom will be ionized. So, and one more thing, let us consider here. Let us consider here. So when I consider a semiconductor in thermal equilibrium, what happens? In thermal equilibrium, so number of electrons will be is equal to number of holes in thermal equilibrium. So before doping you can say, these are the before doping, so number of electrons will be is equal to number of holes. So the number of electrons will be is equal to number of holes in thermal equilibrium. Okay. So when I add a donor atom here, what happens? When I add an acceptor atoms here, what happens? When I add a donor atom, for me, extra number of electrons will come. When I add acceptor atoms here, extra number of holes will come. Remember, these are the values before doping. Before doping. After doping, these are the things extra will come. Okay. So now talk about what is the meaning of charge neutrality. So the charge neutrality, that means positive charge density. Positive charge density is equal to negative charge density. Negative charge density. That means total positive charges will be is equal to total negative charges. Okay. So total positive charges. Positive charges means donor atoms will become positively charged, plus initial number of holes. Similarly, negative, acceptor atoms negative plus electrons. So these are these initial number of electrons, initial number of holes. So after doping, these are the extra things are coming. Okay, so I can substitute what is Nd plus here. So that Nd plus will be, here I have written Nd plus Nd minus Ne. Nd minus Ne. I can write here what is Na plus here. Na minus. So Na minus will be Na minus NH. Na minus NH. If I substitute there, what will I have? Nd minus Ne plus NH will be is equal to Na minus NH plus N0E. Okay. But here for complete ionization, Ne will become NH. So Ne came because of the donors, NH came because of the acceptors. Both are equal. So with this, what I'll have, Nd plus number of holes is equal to Na plus number of electrons. Okay, so remember, this is the important thing. This is the important thing. Okay. I hope it is clear. If you want, you can add law of mass action also here. Law of mass action. So the law of mass action says number of holes, number of electrons is equal to Ni square, intrinsic carrier density. Intrinsic carrier density. Okay. The product of number of holes and number of electrons will be equal to Ni square. In the problem, what they are giving, Nd represents the donor atoms, Nd plus represent the donor ions. These are ions. Similarly, Na represent the acceptor atoms, Na minus represent the acceptor ions. So what is given in the situation, you should be careful. Okay. So thank you for watching my video. Please subscribe and share to your friends.